Hello, am I audible? हेलो।
Yes, sir.
सही
Yes,
आवाज़ आ
sir.
रही है बिल्कुल?
Yes, sir.
बिल्कुल कोई बिल्कुल साफ सुनाई दे रहा है? ठीक है फिर। पीपीटी दिख रही है? हेलो। हाँ जी, कोई बताए
Yes,
पीपीटी?
sir.
पीपीटी
Yes, sir.
विजुअल? ओके ओके
Yes, sir.
ओके ओके। ओके। In last lecture we learned about what is Fermi surface, how to draw Fermi surface, and especially for free electrons. Free electrons means suppose if there is no interaction between the electron and the lattice, then we consider that electron is free. But suppose if we consider, okay, but suppose if you consider that there is no interaction, if suppose if you consider that V is equal to 0, okay, then it means that electron is free. But if suppose there is electron lattice interaction, if suppose there is electron lattice interaction, in that case there is some problem, I think. Okay, if there is a electron lattice interaction, in that case we cannot say that V is equal to 0. Okay, it means if we consider the Fermi surface for free electrons, what we have to consider, we have to consider what will be the Fermi surface for the nearly free electrons. In case of a free electrons, what we consider that the interaction between the electron and positive ion is equal to 0. If we consider that interaction between the electron and positive ion is equal to 0, then that is free electron. And if you consider that that is not exactly equal to 0, then that is not nearly free electron approximation. If suppose, for example, whether you consider free electron approximation or nearly free electron approximation at zone boundary, what happens? At zone boundary, suppose this is the allowed energy level, and at the zone boundary, which is at plus pi by a or which is at minus pi by a, what happens? There is there is forbidden energy gap between the first allowed energy level and second allowed energy level, and this is known as band gap of the material. It means whether you consider free electron theory or nearly free electron theory, what happens? The interaction, generally the interaction of electrons with the periodic potential of the crystal, that creates energy gap at the zone boundary. Okay, wait 1 second, there is some problem.
Okay. Am I audible? Hello.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Wait 1 second. Hello. Okay. In case of nearly free electron theory, what we consider that V is equal to
Yes,
0.
sir.
But sorry, in free electron theory, V is equal to 0. In case of a nearly free electron theory, V is not is equal to 0. And then the interaction of electron with the periodic potential that creates energy gap at the zone boundary. Okay. And whenever we plot Fermi surface, suppose whenever we draw Fermi surface, then that Fermi surface will meet or intersect the zone boundary perpendicularly, or with that angle between the zone boundary and the Fermi surface will be equal to 90°. And one more thing, let us consider. Suppose if you
Sir, you
consider,
have
uh,
stops.
yes, if suppose we consider that V is equal to 0, in that case, these Fermi surface, like here, this will be pointed like this zone bound, the Fermi surface of this type of geometry that will be pointed in nature. But if you consider V not is equal to 0, that if we consider the interaction, I am audible?
Yes, sir.
If we consider V not equal
Yes,
to
sir.
0, then this
Yes,
Yes,
sir.
sir.
here is the sharp corners. But if you consider that there is an interaction, then what happens? This sharp corners changes like this. If you consider the interaction, then this become round shape like this. Later on, I will show you. But simply what we have to consider, that if you consider the interaction between the electron and the lattice, then what happens due to this interaction? There will be, due to this interaction, the corners, sharp corners will change into round like structure. Okay. And if you consider the volume of the Fermi surface, then that will depend upon only the electron concentration. More will be the electron concentration, more will be the volume of the Fermi surface. And the volume of the Fermi surface is independent of lattice interaction. But if you consider the electron lattice interaction, then this interaction causes distortion in the Fermi surface. There will be more distortion if you consider more electron lattice interaction. But the volume or area of the Fermi surface is independent of the interaction. For example, let us consider somewhere we have drawn like this. Let me revise again. Suppose this is the Fermi surface where this is drawn. In this case, this Fermi first brilliant zone is completely filled, and in second brilliant zone, this is a little bit filled, this like this, and we can apply 2 pi by a operation, and then we obtain this like curve. Okay, and this third brilliant zone, these are partially filled. Here we can represent, applying reciprocal lattice vector, we can represent at one point and using periodic zone scheme, because this is repeated in various zone. Then this will be like this, and further we will apply lattice reciprocal lattice vector, this will be like this. Okay. Therefore, in some cases, as we discussed, the This is the first zone which is filled with the Fermi surface, and these are the Fermi surface of the second zone. The filled energy levels, and these are the unfilled energy levels. And similarly, these are the Fermi parts of the Fermi surface of the third brilliant zone. Okay, what we can see here this is the empty, and this is surrounded by the filled electrons. Okay, in such a case, if suppose this is known as the Fermi surface of the second zone and this is the Fermi surface of the third zone, then here this is the empty space. Okay, or if you consider just opposite, like here, in this case, if you apply this operation, then you will obtain like this. If you apply this operation, then these states, outside this is empty and inside this is filled with the electrons. Okay, the inside of the Fermi surface, this is filled with the electron. The condition is just opposite. Here the inside is empty, outside is filled with electron. Outside energy levels are filled with electrons, and here outside energy levels are empty and inside are filled with the electron. Condition is just opposite to each other. And if such is the condition, then this is known as hole like Brillouin zone, or hole like second zone, and this is known as electron. This is a field, then this is known as electron like third zone. Let me again explain this term. Suppose what happens, if suppose these are the energy levels and the interior, these are the field energy levels by the Fermi surface, and inside this is empty. Okay, what happens, suppose we have various energy levels, but we know that up to epsilon f, these energy levels are filled. It means filled energy levels is having lower energy, and these unfilled energy levels having high energy, more energy. Okay, if you consider weak potential, that V naught is equal to 0, then this corner will be not pointed like, this will be round like it. And this is the electron like behavior, and this is also not pointed like, this is like a round like structure, because we are considering that V naught is equal to 0. Okay, and if you consider such a, then the interior, in this case interior is having more energy, in exterior outside the energy is less. Similarly here, if you consider energy is more, here energy is more, and inside these are the field energy level, energy is less. Okay, these shaded region, let us consider this, these are the filled with the electrons, and therefore these are lower in energy. And these unshaded region which are empty, these are having high energy. Okay, and because these all energy levels are filled, such Fermi surface known as, you can say, because these are third zone Fermi surface, then this is known as electron like structure, because these are electrons filled in this, and this is the gradient of energy, which is representing that energy is increasing from interior to outside. And here, because these are the field energy level, these are lower in energy, and these energy levels are high, therefore the this is just the representative. As you go inside, there will be increase in energy, and because these energy levels are empty, then this is known as hole like behavior. Okay, because this is empty, and this is surrounded by the field energy levels, then what you can say, this is known as third zone electron like behavior in this case, and in this case this is known as second zone hole like behavior. Third zone Fermi surface is behaving like a electron like behavior, and second zone Fermi surface is behaving like a hole like behavior. Okay, therefore what we can say, we can represent the Fermi surface in this way. For this we will use Harrison method to construct the Fermi surface. What we have to do, we have to find the reciprocal lattice points of a direct lattice. Okay, and then we will choose a center, and by calculating the value of kf, we will draw a circle or sphere that will represent the Fermi surface. And if you draw a Fermi surface, all the energy levels in this Fermi surface that will be filled, and if you consider the above this Fermi surface, then that all energy levels will be empty. Okay, and this Fermi surface, suppose this is the beryllium zone, this may possible that this completely occupies within the first beryllium zone, or it even can cross first beryllium zone and can go in second beryllium zone, third beryllium zone, and so on. Okay, if you consider alkali metals, suppose sodium, which contains only one electron. Suppose if you consider one energy level, in one energy level, two electron can come. Okay, one energy level can be occupied by two electrons. Therefore, if you consider only one electron, valence electron, then if suppose this is the Fermi energy, then only half of this energy level will be filled. Okay, it means if you consider the first beryllium zone and number of valence electron is only one, and if you draw the Fermi surface, that will completely lie within the first beryllium zone. If you consider one valence electron per atom, then that Fermi surface will completely lie between the boundaries of the first beryllium zone. And because suppose this is the beryllium zone and this is the Fermi surface, and there is the separation between the zone boundary, there is a separation, there is a large distance between the Fermi surface and the zone boundary, and then we can say that there will be no distortion. There will be no, this is the, if you calculate, this is the one half of the volume of the zone. If suppose this is the volume of the zone, then its volume only will be equal to half of the volume of the first zone. It means it lies completely inside. Therefore, there will be no interaction of electron with the lattice, and that there will be no distortion. Okay. Therefore, if we consider the sodium, Fermi surface of sodium, that will be perfectly spherical in nature. आवाज आ रही है? कोई बताता है मुझे? हेलो?
Yes, sir. You are audible, sir.
है ना? नेटवर्क है ना? Okay. Then we can say simply, if you consider the Fermi surface of sodium, that will be exactly spherical in nature. But if you consider the Fermi surface of any other material, for example cesium, then there will is distortion, approximately 10% distortion in cesium. Let us consider, if you consider the sodium, then that Fermi surface will lie completely inside the first zone boundary. Okay, that will lie completely the first zone boundary. That is why we can say that this is perfectly spherical. For example, let us consider this is the 3D structure, and this is the perfectly spherical because this lies inside the beryllium zone. But if you consider calcium, which contains two valence electron, or copper, then what happens? The distance, this is the zone boundary, and this is the Fermi surface, then these two touches each other. Due to this, what happens? There is distortion. Let us consider this is the distortion. We will consider later on in detail, but this is the distortion. There is a formation of hole. Or here, if you consider copper, there is the distortion because these Fermi surfaces are touching the first beryllium zone boundary, and there is the effect of lattice, that is Coulomb interaction, is strongest at the zone boundary, that causes distortion in the Fermi surface. Okay. Therefore, what we can say, if you consider the divalent metal, suppose beryllium, magnesium, and even if you consider very weak lattice interaction, then that will be spherical, but not exactly spherical. That is nearly spherical, although these two are containing two valence electrons. Volume is twice as compared to sodium. Okay, but that will lie in the first beryllium zone boundary. Okay, and that if the volume crosses the first beryllium zone boundary, then there will be maximum distortion. Okay, if suppose some Fermi surface, if suppose this is the, and we are drawing the Fermi surface which is crossing the first beryllium zone boundary, then there will be more distortions. Okay, as I have explained this thing, let me consider again once again. Suppose I can write that force, the Lorentz force acting on the electron, if placed in the magnetic field, can be written like this. Okay, force is equal to this, and the force we can write rate of change of momentum. Okay, and momentum we can write that is h cut k. Therefore, this equation and this force, if suppose you are applying electric field, then this force can be written like this. In case of a magnetic field, that is this. In case of a electric field, the force acting on that is equal to this, and momentum is equal to this. And the direction of k, the direction of k, what will be the direction of k? We can say dk by dt. Now we can derive the what is the direction of dk by dt, that force, if suppose we are applying some magnetic field also, then force is equal to this. This force we can write dk upon dt. Okay, h cut also we can include here. And velocity we will write like this. I will show little later that velocity can be written like this. Then we can say that k will be perpendicular to the gradient of energy, or you can say velocity, and k will be perpendicular to the b. The direction of motion of the electron will be perpendicular to the gradient of energy, where is change in the gradient of energy, and that will be perpendicular to the magnetic field. Let us consider for this, if suppose there is no interaction, suppose that is the we are considering free electron, we can write momentum is equal to h cut k, or we can write mv, that is h cut k, or we can write v is equal to h cut k by m. This is when we are considering that electron is free. Then velocity, here velocity we can write velocity is directly proportional to k. V direction of the velocity will same. The direction of the velocity will be same as the direction of the k. Okay, let us consider this is the spherical Fermi surface, where we are considering that v is equal to 0. There is no interaction between the electron and the lattice. In this case, this is the Fermi surface, then we can say this is equal to k. Okay, and this is the direction of the electron, that is v. This is the direction of the electron. Then we can say that k wave vector and direction will be parallel to each other, same direction, because here we are considering that this is nearly Fermi surface is spherical in nature. But if you consider that v naught is equal to 0, in that case, now this is the Fermi surface which is curved like behavior, that is distorted. Okay, then the velocity will be written as using same formula, that will be gradient of energy upon h cut. This is the gradient of energy. Gradient of energy means where is there is increase in energy. Okay, gradient. If suppose if you consider this is gradient is equal to 0, if you consider that this is like this, then this will be just gradient of energy which is perpendicular to this curve. Okay, and this is the direction of k. This is the direction of k, or you can say that will be the direction of velocity. But in case of, if you consider that Fermi surface is not spherical, then these will not parallel to each other. The velocity will be parallel to k wave vector if we consider there is no interaction. But this velocity is proportional to gradient of k, and therefore the direction will be in that direction where there is the gradient of energy. Okay, and it means in case of a non-spherical surfaces, this may or may not be parallel to each other, depending upon if there is more curvature in the curve, that may not be parallel to each other. Okay, it means, let us consider, suppose this is we are considering whole like orbit. Here electron is moving like this clockwise. Okay, and this is the direction of k. You can say this is the direction of k. And if you find, suppose we are applying magnetic field perpendicular to the plane. Okay, then this is the how to find the this is the k value. We can find tangent to it with respect to this. This is the tangent to this, and this is the gradient of energy. This is the gradient of energy, the force or the velocity of this force acting on the particle. And if you consider hole like behavior, that gradient will increase from outside to inside. But if you consider this is hole like behavior, but if you consider these energy levels are filled, then in this case electron will revolve anti-clockwise, because that is this is behaving as a electron like behavior. Electron like means negative charge, uh, hole like means positive charge. Therefore the direction will be opposite to each other. In that case this gradient will go outside. If you consider the Lorentz force acting on the electron, that will be outside. Or you can say if you go inside to outside, the energy will increase, and this is because inside these energy levels are filled, and therefore this is known as electron like orbit. There are some orbits like this which is known as open orbits. Suppose there is a starting point this from B, then this ends at A, then again this goes to B dash, which is just similar to B. Okay, but there is no closing end. Then this is known open orbits. Fermi surface having open orbits. Okay, and this behavior is in between the electron orbit and hole orbit. This will behave like this. Therefore what we can say, we can classify the Fermi surface in three types. One is let me write here, if that orbit is not closed, if suppose a particle reaching at A point, again that goes to B dash, and B dash is thus back to the B, or B is equivalent to each other. They are connected by the reciprocal lattice vector, and this is simply we are saying that in this case this is open orbit. There is the possibility of formation of open orbit, and this is very important. If you consider the magnetoresistance, in order to explain the magnetoresistance we consider open orbits. And what are the closed orbits? There are the orbit that are closed. If suppose that is having field state inside, then that is known as electron orbits. An orbit that enclose empty states, खाली है अंदर से, then this is known as hole like orbits. Okay, and that open orbits which is open at the end. For example, let us consider, suppose this is the Fermi surface drawn and this is the empty energy level. Using reciprocal lattice vector we can transform all these four energy level here. Then this will be like this. Can anybody tell me this will be electron like or hole like?
Whole like.
Haji? This is hole like behavior, because this is empty states and this is represented in periodic zone scheme, 1, 2, 3 and so on. Okay, for example, what is the meaning of hole like behavior? Suppose if you consider this is the valence band. Okay, up to this valence band is filled, and these are the empty energy levels. Okay, these are the field energy levels and these are the empty energy level. Then this is a hole like behavior. If you consider like this, suppose this is the valence band and this is the field, there is the conduction band, and then if suppose up to this is empty, then this is, it means this is hole like behavior. Okay, it means there are the valence state near the top of the valence band. Okay, that represent the hole like behavior if there is some empty energy levels are available in the valence band. Therefore what I can say, that what are the Fermi surface? This Fermi surface is simply drawn in the K space having the radius K, and that is representing simply that all energy levels are filled, and these are the conduction electrons, all the free electrons. Okay, all the number of free electrons which are occupying the Fermi surface, all the free electrons. If you consider that Fermi surface, suppose that is present in the first Brillouin zone, that will be spherical in nature, and if they cross the first Brillouin zone and go in higher zone, then that becomes non-spherical in nature. And whenever Fermi surface meets the zone boundary, then they meet at right angles. And this Fermi surface is very important. Using this you can explain many property of the metals. For example, heat capacity, polyparamagnetism, electrical conductivity, thermal conductivity, thermal and so on. You can explain many properties using this. Now we can construct Fermi surface using a method which is known as Harrison method of constructing Fermi surfaces. And this we generally use in extended zone scheme. And we will consider two types when we consider that V is equal to 0, and one case where V is not is equal to 0. V is equal to 0 means simply there is no interaction between the electron and lattice, and V not is equal to 0 means there is some interaction, that may be even weak interaction. Okay, if you consider that there is some interaction, if you consider there is some interaction, then what happens? This weak interaction causes distortion in the Fermi surface, and that distortion leads to energy discontinuity at the zone boundary. I will show later on that there will be energy discontinuity at the zone boundary. And generally whenever we construct Harrison method, then we assume that V is equal to 0, or V is nearly is equal to 0. If you consider that V is not equal to 0, then even that case we consider this is very low value, having very small value. Otherwise there will be very large amount of distortion, very large amount of interaction that will cause a distortion in the Fermi surface, and more discontinuity and more distortion. Okay, therefore during the assumption we will consider that the effective potential energy acting between the electron and positive ion, that is very very low. Okay, and there is some distortion at the zone boundaries. Generally, we will discuss the construction of Harrison method, the Harrison method for the construction of Fermi surfaces in two-dimensional and three-dimensional material. Let us, for example, let us start with a very simple example. Suppose we have to construct in two-dimensional material. Let us consider we have a square lattice having periodicity A. Suppose we are considering square lattice having periodicity A, and we have to construct the Fermi surface in two dimension. Okay, suppose let us start. If you consider any, there may be one electron, two electron, three electron, four electron, and so on. Let us consider, for example, we are considering monovalent metal, for example sodium. Okay, if suppose we are considering that the direct lattice is A, then its reciprocal lattice will be equal to minus pi by A, 2 plus pi by A, that is the zone boundary. Or you can say the distance between the zone boundary, that will be 2 pi by A. Similarly, you can draw that will be equal to 2 pi A. If suppose this is, if you consider direct lattice as a square lattice, then its reciprocal lattice will also be square lattice. Here the distance is equal to A, and here that distance is 2 pi A. Then what will be the area of this reciprocal lattice, square lattice? Yes, what will be the area of this? You can say first brilliant zone, because this is minus pi by A to A and so on. Then what will be the area of this brilliant zone? Can we say that this is 2 pi A multiply by 2 pi A? हाँ जी, आवाज आ रही है?
Yes, sir.
ठीक है. Then we can multiply there, the area will be equal to simply 4 pi A square upon A square. This is the area of the brilliant zone. Okay. Now what we know, there is only one electron. Now in one energy level there will be two electrons, but we have only one electron per unit cell. It means only half of the first brilliant zone will be occupied and rest will be vacant. Only half will be occupied. We have calculated that area is equal to this much, but only one electron is present per unit cell. Therefore area will be half. We can write 1 by 2. And if you draw a Fermi surface, because these all energy levels are occupied, because that electrons are present, and we have to draw a circle, in that case we can write the area will be equal to pi kf square. That is, this is the area, that is the kf of the Fermi surface. Let us write pi kf square, then this is equal to this, 2 cancel out, this is 2 pi a square. Or you can write kf square is equal to, divide by pi, we can write like 2 by pi, and this is pi by a whole square. Or we can write kf is equal to this, we can convert like this, then kf is equal to 0.798 pi by a. Pi by a is the zone boundary, minus pi by a to plus pi by a, this is the zone boundary, and the value is 0.798. It means, can I say that kf is less than pi by a? The value of kf is less than pi by a. It means if you draw a Fermi surface where this is from minus pi by a to plus pi by a, what we can say that this is the Fermi surface which will lie completely inside the first zone boundary. The first zone boundary, if you calculate the distance, if this is the center, then this is the pi by a, and this is pi by a. This is the first zone boundary. But the circle radius is only 0.98 pi by a. Therefore, can we say that this Fermi surface will lie completely? This circle having radius only this much radius, this will lie completely inside the first brilliant zone. This will be completely accommodated in the first brilliant zone. And this is very away from the zone boundary. This is not touching or not, this is not near to the zone boundary. Or we can say the Fermi surface, because that does not go to near the zone boundary, therefore it remains undistorted, or this will be perfectly circular in nature. There will be no distortion because this is away from the zone boundary. Okay. Now let us consider divalent metal. Divalent means, suppose if you are considered calcium 2 plus containing two valence electrons. In one energy level, two electron can come. It means we have already calculated 4 pi a square upon divide by 2. Now there are two electrons, let us multiply by 2. That will be the area which is occupied by the electron. Let us represent this area in the form of Fermi circle. Then this can be written as pi kf square, where we can write kf is equal to this much, or kf is equal to this. For the divalent metal, value of kf is greater than pi by a. What is the meaning of this? Can Fermi surface cross the zone boundary? It means Fermi surface will cross the zone boundary or not?
Yes, sir. Second first.
Yes, it will cross the zone boundary. Let us consider the case. This is the kx, ky two-dimensional cases, and this is for the v is equal to 0, and this is v not is equal to 0, but having very low value. Now this is the first zone boundary as we know. And what is the case? This Fermi circle which is drawn like this is crossing the first zone boundary. Okay. Let us calculate what will be the value of this distance. Can anybody tell me what will the value of this distance?
Root 2 pi by a.
Root 2 pi by a. 0.414 pi by a. Okay. What we have calculated, that is 1 point. This is 1 point. Okay. This is 1.12 and this is 1.4. It means this Fermi circle, if you draw this Fermi surface like this will not cross the corner. Can we say like this? This is the corner. This is the corner. And this distance is this much. And the distance we calculated kf is equal to 1.2 something. It means this will not cross this corner point. This will cross the zone boundary, no doubt, but will not cross the corner of the zone boundary. Okay. And if you consider that V naught is equal to 0, it means there is the interaction between the electron and lattice, and that interaction is very low. Then what happens? Whenever, suppose this Fermi surface is crossing the zone boundary, like here, this is crossing the zone boundary, then there will be distortion. Then there will be discontinuity. Let us check. There is a discontinuity appearing here. there is a discontinuity because this is crossing the zone boundary, then in that case for the nearly free electron model we have to consider discontinuous energy levels. Okay, or we can say, let us check this much in the first brilliant zone boundary. Let us check this much is filled, and this corner is empty in first zone boundary. Let us consider second zone. In second zone, this much is occupied, this much is occupied, this much is occupied, and all other zones are empty. Okay, let us consider here. This zone is filled and this corner is empty. Okay, and here if you consider this is the first zone, if you consider the second brilliant zone, then in second brilliant zone this much portion is occupied, this much portion is occupied, and we can apply the reciprocal lattice vector rule. Suppose this, we can brought this term here and this here. Okay, and this is represented in periodic zone scheme. One portion is here, one portion, and so on. Then this is the first brilliant zone, the Fermi surface of the first brilliant zone, which is filled but corners are empty. And here these are the filled but inside this is empty. Let us draw. This is the first brilliant zone and these corners are empty. These corners are empty. And here this is the second brilliant zone and this is occupied. This much is occupied but this is empty. We can say this is empty portion in the first brilliant zone. And if you consider this is the zone boundary, this is the first brilliant zone boundary, and then this is the second zone. Then there are the electron in the second zone and all other zones are empty. Or we can say like this, let us again check. This is the first brilliant zone boundary. Okay, and we are considering that V is equal to 0. But if you consider V is equal to very low, in that case weak periodic potential, then there is a discontinuity appearing at where these Fermi surfaces are crossing the zone boundaries. This is the first brilliant zone band, and this is the second Fermi surface of second band or second zone. But if you consider that V is equal to very large, strong interaction is taking place between the electron and lattice. In that case, what happens? If you apply very strong interaction, then these all electrons will fill this energy level because this is low in energy. This will fill, all this will fill this, and then this first brilliant zone boundary will be completely occupied if you apply very strong periodic potential. In that case, these electrons which are going in second brilliant zone, that will come into first brilliant zone and that will be completely occupied. Okay. Okay, what we have calculated the distance between the center and the corner. That is equal to this much. We have drawn the Fermi surface value of Kf is equal to 1.2 pi by a something. It means this value Kf is greater than pi by a, but this is less than the distance of the from the corner. It means this will cross the boundary of the first brilliant zone, but will not cross the corner of the brilliant zone. Okay, this will cross the boundary of the first brilliant zone, but cannot touch the corners of the zone. Okay, it means if we draw a circle that will go beyond the first brilliant zone boundary, no doubt, but will remain inside the corner of the first brilliant zone. Or we can say even the first zone is not completely filled. Even the first zone is not completely filled. Like this, first zone is not completely filled, and even the second zone is not completely filled. Okay, if you consider V is equal to 0, then there will be no discontinuity at the zone boundary. But if you consider that V is not is equal to 0 or weak pseudo potential acting on the electron, in that case there will be energy discontinuity will appear at the zone boundary. Okay, and there will be discontinuity will appear, and there will be species of Fermi surface that will lie in the second brilliant zone, and by applying reciprocal lattice vector that we can represent at one place. Okay, let us consider. No doubt, if you consider V is equal not equal to 0, there is the energy discontinuity. Whenever this Fermi surface is crossing the zone boundary, and there is the formation of pieces like constant energy surface or Fermi surface at the zone boundaries. Okay, but applying reciprocal lattice vector and using periodic zone scheme, we can brought all these in one place. Like here, this is at one place, and then using periodic zone scheme, we can represent. Now, can anybody tell me this is empty or this is filled level? This level is empty or filled? Haji, am audible or not? Suppose this is the empty level. This is the empty level here, and applying this reciprocal lattice, let us brought this here, let us brought this here, and so on. Then use periodic zone scheme. We can construct. We can represent in many various zones. Then this will be empty or filled.
Empty, sir.
Yes, this is empty. This is empty. Okay, this Fermi surface is empty or filled. Okay, this is crossing the, okay, this is this portion, this is crossing the first brilliant zone boundary, and this is field energy level. Okay, and we can apply a reciprocal lattice vector, and this we can brought here, and then therefore this is the field energy level, and this is represented in periodic zone scheme. Therefore this is the empty energy levels, and these are the field energy levels, and all other outside energy levels are empty. So then this will be hole like or electron like behavior.
Whole like.
This is hole like, and these holes are from the first zone. These are known as first zone holes. Okay, and these field energy levels, this lies in second zone, brilliant zone, and these are the field. Therefore we will say like second zone electrons. These are known as first zone holes, and these are known as second zone electrons. हाँ जी, ये बात समझ में आ रही है? Because these are the field energy levels, therefore these are the electrons like behavior, and because these are the Fermi surface from the second zone, that is why this is second zone electron, and these are the empty energy level of first zone, that is why these are the first zone hole. Any problem up to this?
सर
No problem. Yes, yes.
सर वहाँ पे जो सर ये वाला जो ए फिगर में यहाँ पे जो हुआ है ये क्या है?
हाँ जी, कहाँ पे?
सर ये फिगर ए में ये जो नीचे वाला यहाँ पे ये मतलब शेडेड हुआ है ना,
ये शेडेड सिर्फ ये दिखा रहे हैं कि दिस इज एम्प्टी. Okay, this is empty here. If this is empty, this is empty.
सर ये चारों एम्प्टी हैं.
This belongs to one sodium atom, this may belong to other sodium atom, and so on. This is represented in periodic zone scheme. हाँ जी, अब दोबारा पूछो.
सर ये बी में ये दोनों ही फील्ड होंगे और ये जो साइड में
हाँ जी, ये बिल्कुल फील्ड लेवल्स हैं सारे इन periodic zone scheme.
ओके सर.
Hello, sir.
हाँ जी,
Sir,
they may have represented like this, that these we have transformed here and here, that is why they are representing that these are the unfilled energy levels, but that we can represent in periodic zone scheme, that all where this is field levels. Okay, हाँ जी बोलो.
Sir, for the strong potential, if you apply strong potential, so sir,
If you apply strong potential, then what happens? Simply, due to very strong potential, these all electron energy levels which are present, we can say second zone holes, electrons will fill the first zone a second zone electron will fill the first zone hole if you apply very strong potential, or if there is very strong potential acting between the electron and the lattice, then this second zone electron will fill the first zone hole.
Yes, sir. For this case, first beryllium zone will be occupied, fully occupied.
First beryllium zone will be completely occupied.
For what for the second beryllium zone? Is that fully
Second beryllium zone will be completely empty. Third beryllium zone will be completely empty, and so on.
okay, sir.
Let us consider trivalent metal. If suppose we are considering trivalent, suppose aluminium 3 plus, that is trivalent. Then what we have represented 4 pi a square, 1 by 2 multiplied by 3. And then we can write Kf is equal to this, this and this. This will cross the corner or not?
Not possible.
Still, this will not cross the corner. Even there are 3 electrons present, then still the Fermi surface will look like the same, but little larger, having little larger area. Or we can say, let us draw here. Here you can draw like this. There will be still empty and a little larger circle. Okay, we can draw a little larger circle that will not cross the corner of the zone. That will not cross the corner of the zone. Radius of the Fermi surface is still smaller than the distance of the corners from the first beryllium zone from the center. Okay, Fermi surface will be of the same nature as we have considered the divalent metal, but there will be only one difference. Okay, what will be the difference? Suppose if you draw a little larger surface, then these holes will be smaller in nature or larger in nature?
Small.
The size small, this becomes small. Okay, what will be these second zone electrons?
Large.
That become larger. Okay, this first zone hole becomes smaller and second zone electrons becomes larger. Otherwise, there will be no difference. Okay, only difference will be the size of the first zone holes will be smaller. Size of the first zone hole will be smaller and the size of second zone electron will be bigger. Only this much will be the difference as compared to divalent metal. If you consider trivalent metal atom, then that will be the difference. बात समझ में आई किसी को? The first zone holes will be smaller in size as compared to divalent metals, and the second zone electrons, the size of the second zone electron will be larger or bigger than the divalent metal. हाँ जी, ये बात किसी को समझ में आई है?
Yes, sir.
समझ में आ गई है? Okay, let us consider tetravalent metal. Tetravalent means 4. What you have to do? Multiply by the 4. Then do the calculation. Now the value is this. Now this will cross the first corner of the first beryllium zone boundary? Will it will cross?
Yes,
हाँ
sir.
जी.
Yes, sir.
Now if you draw the circle, that circle will cross the corner of the first beryllium zone boundary. Okay, if you draw the Fermi surface, that will pass through the pass even in second beryllium zone, fourth, and so on. And because that is crossing the zone boundary, then there will be distortion or discontinuity will appear. Let us check. This is the, from here you can check, this is the first beryllium zone boundary. Okay, and this is the Fermi surface. This is crossing, this is the corner. Okay, this is crossing the corner, and here this is for v is equal to 0 and this is for v is equal to very low value. In case of v is equal to 0, this is continuous, it's perfectly spherical. But in v not equal to 0, there is a discontinuity. Whenever these are meeting with the zone boundary, there is a discontinuities. And let us check. This is the Fermi surface, and this even lie in the second brilliant zone. Let us check from this. This is the second brilliant zone. This lying in second brilliant zone, and even this is the second brilliant zone, and these are the portion of, let us check, these are the portion of third brilliant zone. These are going in third brilliant zone also. Oh, sorry. These are the portion of third brilliant zone going to third brilliant zone. Even these are crossing into the fourth brilliant zone. Okay. Therefore, if you draw for the tetravalent metal, then the Fermi surface will cross the first brilliant zone. The first brilliant zone. Now the condition is reverse. This is the Fermi surface, and zone boundary is lying inside the Fermi surface. The first brilliant zone boundaries are lying inside the Fermi surface. But in case of a sodium, the condition is opposite. In first brilliant zone, the Fermi surface is lying in the first brilliant zone. But if you consider tetravalent metal, condition becomes just changed. And this Fermi surface crossing the corner, and this is occupying the second, third, fourth, even fifth zone of the fifth brilliant zone boundaries. Let us consider this figure. This is the first brilliant zone. Okay. This is the first brilliant zone. Can we say that that is completely filled? Yes.
Yes.
Can we say that first brilliant zone is completely filled with the electrons? Haji?
Yes, sir.
Yes, sir.
Yes. First brilliant zone is completely filled with the electron. Let us consider second brilliant zone. This is partially filled. There is empty energy levels. Let us consider third brilliant zone. This is the third. This is only partially filled. And these are the fourth brilliant zone boundary. This is also only partially filled. Okay. It means only the first brilliant zone will be completely filled by the electrons. The second brilliant zone, third brilliant zone, fourth brilliant zone, and so on, that will be partially filled. Okay. Now we have to draw, we have to discuss all things little detail. कर लेते हैं आज यहाँ तक. Okay, the first brilliant zone boundary is completely filled. Let us check the second brilliant zone boundary. This much is filled. We can apply reciprocal lattice vector G. This will come like in here. Then this here, this will be empty. We can apply this operation. Then in the center there will be the empty space. If you transfer the second zone Fermi surface in first zone, then this is known as reduced zone scheme. Then this is empty energy levels. What we can say? We can say that this is second zone hole or electron.
Whole,
Whole.
sir.
Yeah, these are the second zone holes. Okay. Let us consider third zone electrons. This is the third zone electrons. Okay. These are the third zone electron. We can transfer and apply reciprocal lattice vector. Then this will be like this. And this will be filled energy levels. And this is represented in periodic zone scheme. Okay. This is represented in periodic zone scheme. And that is represented in a reduced zone scheme. And now here, these are the empty levels or filled energy levels. Haji?
Field, sir.
These are filled. Therefore, we will say that third zone electron. These are the third zone electron. Now let us consider fourth zone. In fourth zone, this much is the field energy level, and all other levels are empty. And if you try to combine this, that will become circle, exactly circle. हाँ जी, बात सही रहेगी. If you combine these four portion, that will becomes exactly circle. बात सही रहेगी. Then this is like circular like. This is fourth zone. This is hole or electron?
Electron.
Yeah, these are the fourth zone electron. Therefore, second zone Fermi surface will behave as a hole. Third zone's Fermi surface will behave as a electron. And this will be a curve will be like this. And the fourth zone electrons will be nearly circular in nature, and that will be fourth zone electrons. Okay. So what we can say, and if you consider the weak potential, then there will be discontinuity will appear at the surface. Okay, and there will be the distortion in the Fermi surface. If you consider the weak potential, there will be the distortion or breakup at the zone boundary. By applying the reciprocal lattice vector, we can obtain a closed energy curves. Okay, in that first brilliant zone is completely filled. There is no this is filled. These are completely filled energy levels. Okay, and the second zone, third zone, and fourth zone, there are the constant energy curves or the Fermi surface that is appearing in second, third, and fourth zone. Second zone is represented as we represented in reduced zone scheme, that is equivalent to hole like behavior, and the third and fourth zone, which are represented in periodic zone scheme, that show electron like behavior. Okay, in reduced zone scheme, what happens, that we obtain a one closed energy curve that is empty, that is, it means that is hole like. Okay, and the in case of a periodic zone scheme, we obtain second zone holes, and we obtain third and fourth zones electrons. Okay, applying this simple operation, using this reciprocal lattice vector, we can represent various Fermi surfaces even in first brilliant zone boundary. For example, this is the first brilliant zone boundary. We can represent all, that is, this is the second zone Fermi surface, and these are the third zone Fermi surface in first brilliant zone. This is known as reduced zone scheme. Okay, therefore we can say first brilliant zone is multi-valued. In first brilliant zone, we can represent all possible zones, second zone, third zones, and so on, and there will be discontinuity will appear if B is not is equal to 0, or whenever this Fermi surface will touch the zone boundary, there will be the discontinuities or there will be the distortions. Okay, यहां तक मैं आज करा रहा हूं. आपको क्या करना है, बाकी ये सारी चीजें आपको वहाब की बुक से पढ़ना है, वहाब कीटल की बुक से, और आप पढ़ सकते हैं आरजे सिंह के भी बुक से. अगर आपको नहीं समझ में आना तो आपको नेक्स्ट लेक्चर में आप मुझसे पूछ सकते हैं. समझ में आई किसी को बात? नहीं प्रॉब्लम हो तो आपको बताना पड़ेगा. ठीक है, कल आपकी पार्टिकल फिजिक्स की क्लास है, वो कल क्लास नहीं होगी. मैं यहाँ पे हूं नहीं, आउट ऑफ टाउन हूं, तो कल क्लास आपकी नहीं होगी. ठीक है, आलोक कुमार महांता.
Yes, sir.
अंजना विंसेंट.
Present, sir.
असगर अली.
Yes, sir.
अलीना जिमी. अतुल कृष्णा एसवी. ब्रह्मानंद बेहरा.